Okay, so thanks for attending today's webinar that is about the new bridges and gates components of the RiverFlow2D system. And I'm going to start the webinar by giving you some news about the developments we've been doing over the last year or so. Uh, for those of you new to RiverFlow2D or who have been away from our developments in the last uh, year and a half or so, we released last year the new RiverFlow2D engine that we called RiverFlow2D Plus. And it's a whole new finite volume engine that replaces the older finite element model. I will talk a little bit about that today. But also, we released this year in February the new sediment transport module. We have a webinar about that if you're interested. We also released in April the pollutant transport module for multiple pollutants with dispersion and reaction uh, calculation. We also recently released an update of the GPU module, which is still faster what it was before. And I'll have some news about that today as well, of this GPU model. Now we are releasing the bridges and gates components. And as I will describe today, these two new components will be automatically sent to all existing current users. And it will become part of the hydrodynamic module. We are also releasing an oil spill on land module. This is actually an extension of the modern debris flow module that was released last year. But we are working also on an extension of this oil spill on land module for variable temperature that will account for variation of viscosity with temperature. Now, you may have noticed that we are changing the model name from RiverFlow2D Plus to RiverFlow2D. We are moving away from our original name to avoid confusions with some users, and we think that the RiverFlow2D name better reflects the actual model capabilities. We are also very excited about our ongoing development we have. And we are, as I said, working on the temperature-dependent viscosity module for the oil spill on land. We are working on an extension of our present capabilities of the hydrologic model that accounts only presently with constant rainfall and evaporation. We are extending those capabilities to add spatially variable rainfall and also spatially variable infiltration with three different modules that include the Greenamt method, the curve number method, and Horton computation. This is, I think, will be very interesting because we'll allow integrated hydrologic and hydraulic modeling in the same mesh. We are also adding wind stress on the surface. We are working on the user interface of the 1D, 2D module, which I have talked in the past in previous webinars as well. And also in making faster what is already very fast, which is the GPU module. We'll be releasing sometime probably this year the RiverFlow2D in the cloud. And I will talk a little bit about that today as well. But let me give you a heads up of very, very recent tests we have done with the new GPU version of the RiverFlow2D model. What you see here, this bar chart accounts for tests in different GPU cards. This here shows the name of the NVIDIA GPU card. This is the latest generation GTX Titan Black. This is the NVIDIA Tesla K20. These are much more expensive cards. This Titan is in the range of 900 or so dollars. This is in the order of 3,000 or so. This is an older Tesla version that we originally tested a year ago. And this is the GTX 780 that is on the order of $450 on the cost. Just so you have an idea of the cost of each card. But things hardware is in the GPU arena is improving so quickly. We are working on two fronts here. We are getting automatic acceleration due to the new hardware on one side, but we are working very, very hard on the development to make what the code still faster by optimizing in a better way to take advantage of this new hardware, and those two fronts have generated some very, very nice results that I'm presenting for the first time to you today. So these bars here represent results for the Titan Black, this for the Tesla, this for the Tesla 2075, and this for the GTX 780. The green bars represent results for a mesh. And this is a test we made with a mesh of almost 2 million cells. The red color indicate the mesh is 154,000 cells, and the blue is the smaller size mesh that is almost 20,000. So the larger the mesh, the bars indicate the acceleration. So for example, this blue indicates that the Titan Black accelerates the run with respect to the non-parallelized model by 15 times. And as you see here, the smaller accelerations occur for the smaller mesh. So the larger the mesh, the better the acceleration that you get with the GPU version. Now, you see, even with the smaller meshes, you get quite decent acceleration of order of 12 to 20 times or so. But for the larger meshes, you get acceleration close to 100 with the Titan Black card, and in the order of 50, 60 times faster with the medium-size meshes. So this has tremendous implications in actual model use and modeling productivity. For actual projects that used to take many hours, now you can make it in just a few minutes. And for example, in a particular run that we have made, instead of 8 hours, you can do the run in 5 minutes. So you can imagine if you have to do many scenarios in a particular project, the time that you can save with the GPU version, it is incredible. Once you get used to make your run in a GPU computer, you don't want to go back to the CPU version. And this is my personal experience, that all the tests that we do, sometimes checks that we need to make and so forth. And we tend to do everything now on the GPU platform because it's so much faster than the CPU version. So I wanted to give you this latest results that we are actually getting 100% times accelerations. And this is really exciting for users because they get the benefits in the end of this new technology. Now, I want to talk a little bit about the Red River of the North, which is a project we are doing with NOAA. Actually, is a part of an agreement that Hydronia has signed with the NOAA for research and development, and this involves the modeling of the Red River of the North, actually 420 river miles of the Red River of the North in United States. Now we are improving now the data. We are doing a 4-foot resolution LiDAR. By the way, the model is able to handle large amounts of data, and in this case, we are using a 90 gigabyte file for the elevation data for the LiDAR, and we use a decent sampling algorithm to obtain the elevations on each element. We are in our initial test. We have a mesh that is relatively coarse, but it has already 1 million cells, and running a 40-day hydrograph in the latest version takes roughly 2 hours of computer time in the GPU. Now, anecdotally, I want to tell you a short remark on this, that I was in a workshop. Actually, we were given in the ASFPM conference recently in Seattle, and I presented these results to them, and someone in the audience told me that the heckgrass model that is developed for this area takes about 7 hours to complete the same 40-day hydrograph. So what I'm seeing is that the two-dimensional models with the development of this GPU technology are becoming competitive with 1D models. Obviously, you think on a 1D model because it's much simpler and so forth. But when you are dealing with such a complex and large area of this that requires thousands of storage areas and weirs and all kind of artifacts to try to model a 2D area with 1D, that is a big burden in the performance of 1D models. So it's an interesting fact that we are exploring now with NOAA, because NOAA is the main users of the 1D model as well, and this is all part of this agreement that we have with them. Now we are working also very hard in the implementation of the RiverFlow2D in the cloud. And we have a prototype that is not available yet, but it will be available, as I said, probably maybe this year. And it will become available initially as a test platform for existing users. So what we want to do initially is to make this available for free as a test for the GPU platform. So an existing user that would have a set of data that want to test and experiment by himself how fast is the GPU version, they will be able to access the RiverFlow2D in the cloud with this platform. So the idea is that you would construct your data files with the mesh, you generate the mesh, enter your boundary conditions and so forth in the usual way, and then import this to the web using this button here. You select the files and then enter some additional information, the simulation time, report interval, managed factor, if any, and then you run the model. You can select also the export if you want to export in standard Argus One files, or if you want VTK files to be post-processed by ParaView, for example, and then you can run the model. Then when you're done, or when the computer is done, it will email you telling your simulation is completed. So you forget about it, you get an email, your simulation is completed, go ahead and download your data or your result files, and you analyze the results, the timing, and all that. And this, as I said, will be initially free as a trial for existing users that would be able to develop the mesh outside in their local computers. So we are really excited about this. We are in the testing process. We already have a server that is presently at the University of Zaragoza, and we'll probably have a second server at the Hydronia offices with similar characteristics. It will be equipped with an NVIDIA GTX Titan Black card as the one I showed you before with the fastest results. And this is a high performance computer that will be available initially through the cloud. So that's about new RiverFlow2D in the cloud developments. Now, for those of you who are new to RiverFlow2D, very briefly, I want to introduce you to this evolving and developing system. RiverFlow2D is a model to obtain detailed riverine velocities and depth in floodplains or rivers. You can use it for floodplain and urban flooding, dam break analysis, sediment transport for erosion deposition, mud and debris flows, pollutant transport, and it has integrated with a GIS GUI, which is the Argus One. You can also use the SMS system, Aquaveo SMS, alternatively, and we provide a link to that system as well. Now, the main characteristics of the model is that it's based on a flexible mesh numerical engine, which is the finite volume model. It's a fourth generation finite volume engine that I can tell you that is with all assurance, that is the most advanced numerical model that you can find today in the market. It provides incredible accuracy with volume conservation errors that rarely exceed 10 to the minus 10%, and 10 to the minus we say 10 to the minus 12. I say 10 to the minus 12 because in rare occasions reach that level, but it's always almost always in the range of 10 to the minus 14, which is actually a number so small that it's on the range of the numerical precision of the numbers that you may use in any computer. It has a very, very accurate wetting and drying algorithm. It handles supercritical, subcritical flows and mixed flows, always in triangle cells or elements. It's fully parallelized. Even the CPU version is parallelized for the with multiple core computers, and obviously the GPU version is much faster. And as you see here, we had here 85x, which was our previous highest mark. We are getting 100 times faster now with the test that we just finished. This is the type of cards that you may use for GPU versions. Now we have a bunch of reference that we can quote, and we can you have in the manual full detailed reference that you can consult on the numerical. All the numerical algorithms that have been implemented here, and you can find all the details in peer-reviewed publications, including the testing, all the details of the numerical methods, the advantages, all the implementation details are included in all of these publications. Now, the mesh generation that you will need is provided by Argus One, the Argus Open Numerical Environment. You get an automatic generation of flexible meshes that can be adapted to any complex geometry. You get statistics of the mesh quality with when you generate the mesh and so forth. You have multiple hydraulic components like Colbert calculations, not rating curves, but actual calculations of discharging Colberts of circular or boxes type. You have the older bridge pier drag forces, which is a very, very simple pier component that we still have there. The weirs component, internal rating tables for simple calculations of internal hydraulic structures, sources and sinks, and rainfall of evaporation and evaporation. The model offers a number of input formats. I won't go into the details of this, but it's a wide variety of input formats for elevations and other data that you need to enter, including GIS data, shapefiles, and so forth. The output is in form of graphics. That's the one you see here on screen, that this is generated with ParaView using directly VTK files from the model. But you have full text output in tabular forms, graphics of many formats, and you have also shapefiles that you can import in any GIS program as well. You can also automatically generate animations or Google Earth animations, standalone VMV video files, or KMZ, KML files as well. Now, in regards to the internal hydraulic structures, the only way we had in the past, besides the culverts, for more complex kind of hydraulic structures, the only way we had was to use internal rating tables. Now, internal rating tables is what we call maybe a Pursman hydraulic structure, because you have to generate a water elevation versus discharge for relationship for that hydraulic structure. And obviously you can define an internal polyline, which is an artificial boundary, but it has some drawbacks. It requires calculations to construct that table, and those calculations need to be done outside. And usually what people were doing was to use a 1D model like HECRAS to construct the rating table. Now, it was kind of frustrating for us to be using a 2D model and then go to a 1D model to calculate a rating table and then impose that rating table as an internal boundary condition in the 2D model. So you were essentially losing many of the advantages of using a 2D model by doing that. So in many cases, that generated results that were incompatible with 2D flows. And also the rating table is not able to handle tailwater control or submersion. So if you have a set of bridges that interact because they affect each other, and you have tailwater control, you have no way to account for that in standard treatment with internal rating tables. So um, we implemented uh, the component that I'm going to present today. So why would you need bridge hydraulics in 2D? Well, there are many, many instances where you would need to better approximate the river hydraulics in 2D. Well, first, in many instances, you have multiple paths and flow directions in the bridge and in the urban area that would um, require using a 2D model. You have bridges of very complex geometry. You have also bridges that are relatively short, but in an instance like the one you see in this image, you have in the same bridge, you have one area that is flowing maybe under pressure and one is overtopping on the same bridge. So if you have the constant water surface approximation that you have in a 1D model, you cannot account for these situations where you have a pressure flow or even free surface flow on one side and pressure flow on the other, or overtopping on the other side. So we wanted actually to implement a method that would be able to handle much more realistically the hydraulics of river bridges. So the main capabilities of the new RiverFlow2D bridges component is that it can handle first arbitrary plan alignment. So if you have a curved river bridge like this one, where you have a complex geometry and the alignment is a curve, you can enter the river bridge in that alignment, exactly following the the bridge plan that you have here. And this means that maybe the velocity in one side is different from the other, so it would be impossible to deal with this kind of bridges in 1D. And using a rating table for this would be totally unacceptable. We wanted also to implement, that it is implemented in the bridges component, a complex bridge geometry. So if you have a geometry arc bridges with piers that are not standard straight type, of you have very complex bridges like this form or any form, almost any form, you can implement it in the new version. The river can be flowing in one side or everywhere, anywhere with a free surface like this. It can have pressure flow, it can have overtopping, and it can have combined pressure flow and overtopping. So you can model virtually all the hydraulics of the river in 2D. Now, let me tell you very briefly about the technical details of the implementation. I will not talk all the details, and I will refer to you to a reference where this is very, very well explained. But just to show you a little bit about how this works and how it was implemented, I will tell you a couple of things. First, the numerical formulation is based on the friction term, the numerical solution of the friction terms written in three different terms. This is the source term of the shallow water equations in 2D. You have the pressure variation due to bed slope or bed variations here. The bed shear stress that is also acting on the bed surface. And also, which is really, I think, a novel addition in 2D calculations, you have local energy losses in 2D. So we account for all the friction generated by the bed changes, the friction on the bottom, and also the local energy losses. And all of these terms are implemented numerically using the finite volume method. And the way the model is implemented accounts for the flow locally in between two cells across the breach. So assuming that this line, for example, is the breach that can have any form, it follows actually any polyline that you define on the mesh. You have cells at both sides, and the computation goes in a way that calculates the discharge and the losses and all the variables in between these two cells, all the cells, and then integrate the whole discharge for the whole breach for reporting purposes. So you get a local calculation, and the local calculations is based on the local geometry of the breach. So if it happens that these two elements fall in for pressure flow, maybe you have a pier here or any other form of the structure, that geometry will be computed and used for the calculations locally between the two cells across the breach. So it's a very detailed calculations that goes on when you implement a breach in RiverFlow2D. Now, if you want to know and get into the details of how this works, you have this reference here that explains all the numericals and also testing. And some of the testing I will show it to you today. Now, to check that the numerical implementation was accurate and sound, there were a number of tests that were developed, and there are many, probably more than 200 tests, and for sure more than 200 tests that were done in the laboratory initially to make sure that the model was working properly. And all these tests were done at the University of Zaragoza in Spain. And as you can see here, the breach geometry that we're used is very varied. You have standard breaches of these forms with internal piers, abutments, arc type bridges in different forms, boxes, and a number of structures. So measurements were taken of the discharge, water surface elevation upstream, downstream, head losses, and so forth. And comparison was made with the model with the actual measurements, and also HEC-RAS calculation was done for each of these particular structures. So we have comparison with the experimental data and also with the HEC-RAS computation. So there were approximately 207 experiments in this particular batch. And the Flow2D implementation, which is actually the method that was implemented in the breach component in the RiverFlow2D model, generated a very, very, very good comparison with the experiments when you compare the depth upstream from the breach. So you get a 0.99 correlation factor between experiments and simulation. As comparison, the HEC-RAS computations for exactly the same experiments gave not a bad results, but it's a little less 0.95 than the RiverFlow2D. And the reason that this is so is because in some of these cases, the 2D approximation provides a much accurate representation of the hydraulics in the actual breach. So it's much more realistic in general to use the 2D model than a 1D approximation. Now, some further testing or more details on the testing. This is for free surface flow. So all the water is going under the breach. There is no pressure flow or overtopping. This is the breach deck. And these are some of the breach geometries that I showed you before. This is the charge. This is the actual depth data. This is the RiverFlow2D depth, HEC-RAS depth, and these are the errors. And the green the green color indicates where the model is, what model is better. So in this case, for these geometries and these discharges, the RiverFlow2D bridge components is better than, gives better results than, and sometimes much better than the predictions in HEC-RAS. There is this case, the rectangular form of the river that the HEC-RAS gives better than the RiverFlow2D. In pressure flow, it's a mixed comparison. These are the errors. In any case, you see that the errors are very small or relatively small with respect to the measurements. This is a more complex case where you have a pressure flow. And in this case, for these geometries, you get similar but somewhat better in the HEC-RAS. And then for these more complex geometries, you get better results in the RiverFlow2D. But all in all, the model seems to be working pretty good with respect to all the tests that were done. Now, how was this implemented in the actual computational model? Well, we added layers for the bridge, the bridges. So you have a new layer for the bridges component. You enter the bridge, any geometry, any polyline that follows. In this case, you have two rectilinear bridges, but you can have any form. Then you enter the bridge ID for each structure and a data file that represents the bridge geometry. Now, the bridge geometry, you can edit that. I will show you. You have also in the new RiverFlow2D data input program, new panels for the bridges and also for the gates. I will talk in a minute about that. And then in the bridge panel, you see the table for the bridge data, but you can edit this graphically. So you can change the geometry graphically. You see the coordinates here. This is the cross section. This is the bed elevation. These are piers here. This is arcs. This is the deck of the bridge. And when you move these points here graphically, this table is automatically updated. So you can either change the numeric values here, and those will change the actual graphics here, or you can change the graphic by dragging the points, and that will also update the numbers here. And then you can save the final data files. So with this geometric editor and the way this built, you can create really complex river bridges geometries, and you can have in holes and in parts of the bridge and so forth. So it's really neat. When you run the model, you get a very comprehensive output. So there are many files that are created. Some of them are in the form of this tabular output to standard output. In this case, you get the hydrograph and water surface elevation for every report interval at each bridge. So you get what's the actual discharge crossing the bridge at each time, and the water surface elevation. This is obviously the average water surface elevation across the bridge. But if you create a cross section on the bridge, you can also have the actual variation of the water surface elevation on the bridge. And if you draw, for example, a profile, and this profile can be, let me go back here. If you create a profile on this example here, across this area. And this is an actual test that we did in this project. You see the effects of the first bridge and second bridge. And these are, in this particular example, these bridges are working under pressure and some of them overtopping. And you see here what's the big impact on the water surface elevation that this structure has on the flow. So it's really exciting, this new RiverFlow2D tool. It will be available on August the 20th officially. It's already on beta for some users have received on beta form, but it will be automatically included in all for all subscriptions, current subscription users that we have. And obviously will be included also in the standard hydrodynamic model. And yes, it works on the GPU as well. Now, the gates component, which is also being introduced today, and it will be also becoming available in the new release update that is coming on August the 20th. It accounts for sluice gates that can have an operation, can open this in a certain way, and it can become part of these complex structures as well. So the gates components can handle also, as the bridges, arbitrary plan alignment, free surface flow or overtopping. It has very simple data. You give the crest elevation of the gate, the height of the gate, H gate, and the aperture time history. So you give the operation of the gate, how it opens or closes in time in a data file. And you can model free working like a weir type of flow. It can work under pressure like this, like a typical sluice gate, but also it can overtop, so you can model the flow over it and down and account for submergence. So you can model all the typical gate operations and in 2D, because if the gate is in the form of a polyline in plan, you can model that as well. Now, how's that implemented computationally in the model? You create a gate in the gates layer, and that gate has a number of data. Well, the ID, the file name of the aperture that gives you the time series of the operation of that, how the gate aperture varies in time. The crest elevation, the gate height, and the gate discharge coefficient. This is something that is being tested now. It's not implemented in the release version. It's hardwired for the release version, but we plan on doing this in the near future as an extension for a more complex gates component. Okay, so also we have new panels for the gates. As with the bridges, you select them here. Okay, so I will entertain some questions in a minute, but let me tell you a little bit about some licensing of this tool and other tools that we have in the model. Also, some special offers that we want to announce today for you. Well, the bridges and gates components will be distributed with the basic hydrodynamic model. Will be integral part. It will not be an add-on. We thought about that, but we think that this will be such an useful tool for most users that it made sense to add it or include it as an integral part of the hydrodynamic model. So it will be same pricing. It will be no additional cost to have this tool. So if you are an existing user, you will get this for free. It's no need to pay for additional module, and it will be free for all current users. Now, in general, for the RiverFlow2D model, we offer single-use licenses, network licenses. We are not doing upgrades at a cost anymore. We changed to a subscription-based upgrading and technical support. So if you purchase a license, you get free upgrades and updates and technical support for a full year. And if you want to continue getting new versions for free, or no additional cost and technical support, you pay the subscription that is 15% of the license cost per year. And that is a very cost-efficient way to be up to date all the time and get the technical support that many users appreciate that Hydronia provides. We offer a 50% discount for academic users and class versions. Actually, the class versions is a lab version that can handle 20 to 25 different users. So it's a network version. So users of the academic versions get 2 single user keys and 1 network version for the network class use. And it's 50% discount. We offer also the RiverFlow2D LT. Now, this version will also include the bridges and gates when it's ready on or released on August 20th. And we offer a special pricing for government agencies and not-for-profit organizations. Now, we have some nice, very, very nice, I would say, news for all users. And it is that we are starting today, we are offering for a limited time the full RiverFlow2D GPU license for a very incredible price, only a little more than what cost is a single user version. You can get the GPU license, and the cost is $7,795. And this is a great discount with respect to our standard pricing. But we want to make the GPU available for as much people as we can, because we believe that this is the future, and eventually all the versions that we and the modules that we have will be in the GPU platform, and the CPU will be essentially an entry-level version. Now, any existing CPU users, meaning any users of the RiverFlow2D model now that want to upgrade to the GPU module can do that for only 2,600, which is a significant. If you remember the old prices, this is a very, very significant discount. And of course, this will include the bridges and gates components. That's an integral part. We also want to get your feedback on the RiverFlow2D on the cloud. We're very excited about this. If you're interested in participating on this, and initially will be limited to RiverFlow2D users, old or new users, because you will need to create the meshes on your own, on your local computer. But if you're interested, please drop us an email to riverflowweb@hydronia.com and let us know your interests, kind of projects you have, if you would be interested in this type of services that, as I said, will be free for testing for initially. But we want to hear your comments and your interest on using this particular platform. If you're interested in licensing and pricing of the model, go to www.hydronia.com. or contact our sales at sales@hydronia.com. Um, now, well, the server that we will provide is uh, is based on the Titan Black, and this is again the name of the email. Okay, now I want to have the opportunity to answer a few questions. We are over the time already, but I would be happy to answer some questions. And let me go to the chat and questions panel to answer your questions. So let me see. I have a few questions here. Uh, okay. Okay, I have a questions about the choking conditions due to river blockage. I understand that you are talking about the condition due to debris that can choke the river. That's not implemented in the present version that will be released. It could be a future enhancement to determine. You can do that with the rating table now, because the rating table can be in such that when you reach a certain water elevation in the river, you can put a zero discharge through a part of uh, the structure. But the calculation that are done now that do not account for that. But it would be an interesting thing to add in the future. Um, I have a question here. Will you be able to set up the bridges using the SMS interface? Well, it probably it will be possible in the future. It's not possible in this release. However, you will be able to set the basic spatial mesh in SMS and complete the rest of the geometric parameters of the bridge using the data input program that is also included in the SMS interface. So in the meantime, you can use the RiverFlow2D data input program as I show you to edit the geometry of the river and run the model from there. And then use the SMS as the standard spatial um, representation. Okay, I have a question here. How can we make the mesh? Okay, the mesh is very easy to set up in the RiverFlow2D model. Just so you for those of you who are not familiar and with this, in the case of, for example, if you have a model like this, um, uh, what you need to do is to have a contour, external contour, that is the extent of the mesh. You enter the bed elevations, and then you select the element size and generate the mesh. And the mesh can be refined very easily by adding polygons or polylines. So, for example, if you wanted to remesh with a higher resolution here. So, for example, I have 20-meter resolution in general, and I want 5-meter inside this polygon. You remesh, and then you have a much higher resolution here in this area of the polygon. So you have a whole set of tools that you can use to generate the mesh, and the mesh also around the piers. So actually, you can still continue counting for the bridge piers with resolution of the mesh around the piers if you want it. Okay. Can you import an SMS mesh in Argus One? Yes, yes, you can. You can actually create the element connectivity and the element. You have to maybe tweak a little bit uh, the file, but it's not complicated at all. It's very easy to recreate a mesh. Actually, when you run the model now, any in SMS or in Argus One, when the engine runs, it will create the contour of the mesh in a file, what is called the domain outline. So this polyline is created in when you run the model. You get the bed elevations and you get the boundary condition polygons that you would need to use in Argus One. So if you run an SMS model and you want to recreate the mesh and the boundary conditions, you can do that in 3 minutes. Okay, I have another question here for the cloud. Okay, if you okay, yeah, well, yeah, the cloud option. Now, remember, this will be initially a testing platform, so and it will be free. So you will be allowed to use it with a password. You will enter your data there. You import the data. You make your run. You finish, and then you are out. Next user comes to use it. There will be a list of users that will be interested in using this. We initially have one server. We will add more servers as the interest grow. But yeah, it will be a list of users. And the price I gave, this incredible offer that we are starting today of 7795 is for a single user CPU. Okay. I have. Okay, there is a question about the acceptances of FEMA, of the RiverFlow2D with FEMA. FEMA, as FEMA announced last year in the FMA conference, FEMA announced that is a new operational procedure draft that is in discussion now, that is getting rid or is planning to get rid of the FEMA list that was announced at the FMA conference in Anaheim last year. I have no news about what if it's already approved or is under review or what's the status of that. But the idea is that any local of government agency that is doing a flood insurance study or a flooding study that wanted to get approval of FEMA, it would be able to use any model with an attached document and testing that ensures that the model has been tested and is accepted by the agency. And if that would occur according to this new operational procedure of operational guideline of FEMA, then any model would be potentially be able to use. So I don't think FEMA is adding any new models for their list anymore. So I think they are waiting for that operational procedure to be in place, and that will open the route for many new models that are probably much better than the ones that are already there, which are just a few. Okay, I have a question here. The result file on the server will be huge. How long does it take to download it from the cloud over a million cell model? Well, it's not. There will be a limited set of results that you can download. You can download results for each particular result interval. We don't anticipate it will be a tremendous time, provided you have a decent bandwidth. but well, we'll help on that eventually. The bridge geometry file can only be created by in Argus One. No, no. Actually, Argus One does not create the geometry file. The geometry file is a simple text file that represents the geometry of the bridge. You can create it in any software, or in this tool that I show you here on the presentation is not Argus One. This is the data input program that is available for every this. Let me go back to here. This you can create this table in any program. It's a very simple representation. It gives you the polylines for all these geometry lines. So you can create it in AutoCAD. You can create it in any program, and then put it in this format and import it here. So it's open to it's an open text file that you can use. Um, I have a user here that wants a clarification on how the SMS RiverFlow2D users can use the bridge module. Okay, uh, so presently with the user interface link that we have with SMS, there is no possibility to create the bridge module, the bridge data inside SMS. Now with the new version, what you will be able to do is create the spatial plan of the bridge. That means the polyline and mesh that accounts for the bridge. Once you have that, the standard SMS RiverFlow2D link can export all the files that you would need for the basic bridge. Then using the data input program, once you have the spatial data, now you are in the same page as the Argus One because you already have the spatial representation of the bridge. And what you need to add only is the geometric representation of the bridge that you cannot do either in Argus One or SMS. You do it with this interface, or you create it with another program outside, because it's a simple geometric file with numbers here that represent the coordinates of this the polylines that represent the geometry of the cross section. Now, this geometry, when you change the numbers here, you can see how they change here graphically. So you can check for errors and so forth, and use it either in Argus One or SMS. It will be exactly the same thing. What are the maximum number of grid cells handled in a given model? Well, we have run several million cells. I think 6 million would be. I'm not sure it's a limit of the model. The model is technically unlimited in regards, in the sense that it doesn't impose a limit. It's probably limited by the available memory that you have, and so typically there are many models nowadays. We have users with 1.5 million elements, 2 million elements, 1 million elements. That's very typical nowadays. Probably most of the projects that I know of, and in our experience with their users, they are on the range of 500,000, 600,000, 300,000, that range. And that's more or less the typical. Okay, I have another question here. The two directions, such as river pressure flow and overtopping, is mostly dependent on the river bed elevation, but some river crossings cities with link banks and level bed. So still this model can apply? Yes. Yeah, you can, because the model will handle the geometry based on the mesh, And if the mesh is resolving the cross section, and if it's variable across the cross section, if the banks, where the bridge, or how the bridge links with the banks, it virtually any geometry can be handled here. So, and as I said, as you saw here, the geometry can vary along the cross section, so you can handle very, very variable riverbeds and so forth. Well, I have a question about the presentation will be available in PDF format. Yes, and in the video as well. Let me see. I have a couple of last questions here. Oh, this is a very interesting question, and about the confidentiality or the privacy of the data on the cloud. Well, yes, the data will be totally private to you. We will sign, if the user wants a non-disclosure or confidentiality agreement, so that your data remains safe and private to you at all times. We only access the data with the user permission. And if we don't, if we get user permission to review the data, because sometimes, actually very often we get data from users to check results and so forth, and that is possible as well. Okay, so I think that's all for today. I really appreciate your presence today in the webinar, and if you can, you have any questions and so forth, just let me know. We're really excited about all these developments, and we have many new things coming up. And I hope to see you in a new webinar. Thank you very much.